Happy Friday, everyone. Today is February 15th, and this is episode 45 of Get Your Tech On, our show on all things DOCSIS. I'm Brady Volpe, founder of Nimble This and the Volpe Firm. With us today are three amazing guests: John Downey, CMTS Technical Leader at Cisco; Asaf Matatyaou, Vice President in Solutions and Product Management at Cable Edge Business at Harmonic; and Tal Laufer, Director of Product Line Management of ARRIS. Today's topic is a follow-on of last year's popular R-PHY and DAA show. Asaf and Tal are each going to cover a nice... So the great thing about this, they're going to cover a nice overview, not just of the sort of the technical of, R-PHY and how it could technically feasibly work in the field, but it's going to be more of a, hey, R-PHY is actually live and it's out there, and we're going to cover those things. And John and I are going to go over and dive into nuts and bolts with Tal and Laufer. So this is a fantastic panel. Super, super excited about this show. So I want to say hi to Tal and welcome her back. Tal, so good to have you back with us. Thanks, Tal. How are you been?
Good. How are you guys?
Doing great. Good to see you.
Yeah, you too.
Asaf, so good to have you back. How have you been?
Very well. Thanks for having me back.
Outstanding. Good to have you back. And John, so good to see you as a stateful product of our show.
It's always great to be on. Thanks.
Thanks, man. Thanks. So before we get started, I do have just a couple of things that I saw interesting in the news from my standpoint. We have an announcement from Google Fiber that they are they're actually going and pulling out from Louisville. So they're leaving Louisville. I think this is kind of interesting. There's some interesting news in this. Google Fiber launched in Louisville in 2017, but they say various obstacles have caused issues for them. One of the ones that I heard about was they were burying their fiber just a few inches under the ground, and so they're kind of not living up to the standards that they were talking about. I think this kind of illustrates that cable is a bit more difficult than what people really understand it to be, and so they've had failed attempts and they're pulling out. So this, I think, is just an interesting topic. It's good for us as an industry, people who really understand cable well. And don't know if any of you have any comments on this or not, or thoughts on this, but for me, I think it's an interesting topic just to discuss, that when you're trying to enter into the industry, it's not that easy. So any quick thoughts, or should I move on? Okay, I'll move on. Another.
Hey, I always have comments.
Okay, John, go ahead. You're welcome.
It kind of reminds me back in the day when AT&T got into it, but with their unions and their costs, and it was a lot more difficult than they thought, right? And then Comcast came back around. It was TCI to AT&T to whoever. But I think Google is achieving exactly what they intended to do, and that was force our hand. Force everyone to upgrade to faster speeds so people could have a higher, bigger pipe to use their services. Google is not a service provider. I doubt that they ever wanted to be.
Yeah, and I think a lot of people,
how serious they were.
A lot of people said that about Google to begin with, that, what is their objective? And they were pushing a lot of speed. They were getting in just kind of a couple of niche industries, or niche markets. Atlanta was one of the niche markets that they are in. And they've also said they're not expanding any further in Atlanta. I think they're pulling out of the couple places that they were in Atlanta, but they did put pressure on all the operators that were in the markets that they were in. So, hey, if they're pulling out at this point of those markets, fine. But the operators that were in around where Google Fiber was definitely had to up their game.
Yeah. And I got one more comment. Is it Louisville, or Louisville? Which one are you talking about?
It's Kentucky.
Well, then it's Louisville. You got to say with a mouthful of marbles.
Yeah.
Get it right.
I'll take your word on that one, John. So, any other thoughts or comments on that? Are we good on that one? because I've got another one I want to queue up, and this one, John, is for you, the man with the worst internet connection in the world. This one is coming to us from MIT Technology Review. This is why the future of satellite internet might be decided in rural Alaska, and this is just talking about how advances in satellite are coming along. That 11 months out of the year, you can catch Christine O'Connor working at the Alaska Telecom Associated in Alaska, and they're really just focusing on, people in rural areas, John, who have very little internet connection. They're really looking at this opportunity to gain satellite connectivity because they don't have access to other internet connectivity. I also know that Elon Musk has a huge investment at having very low low satellites moving around the world to deliver internet to people.
Leo?
Yes,
Leo.
Thank you. And so these are great opportunities. I think the interesting thing will be how these, putting satellites in low Earth orbit, thank you, Leo, will compete with us as an industry. I think it's going to be a really interesting thing to see moving forward, something to be definitely worth monitoring because it can be really a game changer for us as an industry. So that is something I see as, very exciting technology-wise, but could be a total game changer for us. From your standpoint, John, it could be awesome for you because you won't be using dial-up and your challenges that you have on the internet.
But, I think it's really focused for the rural America, rural areas throughout the world. So the big cities will still have fiber as deep as possible, getting deeper. But, wouldn't you still have problems in urban areas with buildings and not line of sight, but, you have a lot of buildings that even screw up your GPS when you're trying to get maps to work when you're going through downtown New York. So there are some hurdles there that they already have fiber. So I'm sure that announcement probably not going to affect them in big cities.
Yep. Yeah, I totally agree with you. I think the masses are going to absolutely still require wired connectivity unless 5G fills that gap or there's some, really amazing technology, but it's going to be very difficult to deliver gigabyte per second data speeds over and do it really, really solidly with low latency and do that over a wired connection. We were talking just before the show, Asaf is, dealing even in his own home with good Wi-Fi connection is having breakups and stuff. And we see that all the time. That's why a wired connection is really, really hard to beat at any time. So satellites are great. Wireless connections are great, but they break up over time. So yeah, that's great things. Awesome technology, but wired is still hard to beat. And that's why we're having this topic today on R-PHY and DAA.
But as consumers, this is great for all of us, right? Having choices that keeps driving the industry forward and coming up with better ways of doing things. Even satellite, I suspect, they're probably looking into their latency issues and trying to find new either technology or new protocols to get around it. And then that can transfer into something that we might be able to exploit, right? Even DOCSIS 3.1, OFDMA, we took that from wireless and other industries, other disciplines. So you know what? That actually works pretty well in their environment. So let's adapt it to our own. So here we go with DOCSIS 3.1 and a new modulation scheme. So, it's good for all of us.
Yep, absolutely. So
I want to add to that. I think the other challenges people have, even if you have an incredibly high-speed connection to your home, which I'm confident I do, is the Wi-Fi network inside the home. So you can have all these great, so whether it's satellite or wired or fiber to the home, within the home, people are not going to connect through their, all the different various devices they have over a wired connection within the home or within the business. Everything is wireless. And then you got all these Wi-Fi signals that are potentially not strong enough or interfering with each other. And I wonder, I don't have any statistics, how many people are calling up their cable or service providers complaining about, lack of speed or issues. when it's potentially driven by their Wi-Fi network. I know for me personally, I've tried to upgrade my Wi-Fi network in the home recently. Again, the wired connection is amazing, but within the home, it's always a challenge to get it right in all corners of the home. And with all the devices trying to connect, should I use extenders? Should I use a mesh network? Probably not a topic for this session, but I don't think that the solution ends at the pipe into the home, but there's or to the business. It's within the home and within the business as well.
Yep. Yeah, I mean, the number I've heard is like 60% of a lot of CSR, TSR calls are related to just Wi-Fi issues. It was never the DOCSIS network to begin with. So I think you're right. It's a good topic. We could spend another hour on that alone. So very good topic. So, hey, with that being said, I would like to start and give some time now, starting with Tal. Tal's going to give a presentation, parts of a presentation that she gave at Expo, and then Asaf will move on to you. I want to open up the opportunity for Tal to do that now. And again, I think the reason that these presentations are so important and R-PHY is so important, I had a really interesting conversation last week with an individual, go unnamed, but he was, kind of focused on the telecom industry because thought cable was going nowhere. And he said, he was reading how R-PHY was just really changing the game for the cable industry because it's just giving us so much expanded reach. And so again, we talked, I think, about a year ago on this, and now I think we want to get in. A year ago was so much more theoretical. Now I think it's just so much more practical because we're getting into that. So with that, I'd like to queue up Tal and give her the opportunity to go into her presentation. So Tal, with that, please enlighten us with what your findings are now at this point.
I will try, Brady. I'm not sure I'll be able to make it, but wow, what a year can make in terms of difference on where we talked about remote PHY about a year ago and today, right? About a year ago, a lot of it was theoretical. There were almost no remote PHY deployments out there in the world. Now we are starting to see some real deployments. We're starting to tackle some new questions, actual questions that come from the field and from actual customer experience. So this year has been critical to get our hands and feet wet as much as possible and be able to see that in action and be able to also resolve some issues in the field. So the presentation I have for today, and I'm going to start presenting here, it is taken, as Brady mentioned, from the Cable Tech Expo event this last year. And I'm going to show kind of a shortened version of it, right? Because we don't have enough time. I think you can see my screen okay. So title of this talk was It's Alive, Getting to Successful Remote PHY Deployment, the Do's and Don'ts. And I had two very distinguished partners for this paper with me, Jeroen Putti and Uffe Kelsen. Jeroen is from ARRIS and Uffe was from Stofa, which is the operator with which we had this experience. So I wanted to tell you today not much about why how remote PHY works and all that. We've done this in the past. So today I'm going to focus on how did it work, right? What did we learn from initial deployment of remote PHY? So this is kind of a timeline of the entire project, right? And a picture worth 1,000 words. So we started it in October 16 or so. The deployment itself started in March 18, and we're going on deployment, pretty fast. So we've got quite successful and substantial deployment there. It took a while, right? So if you remember, October 16, that was 2.5 years ago, was more the beginning of the remote PHY spec, and there was a spec back then, but it was not completely finalized. There were still some additions that were going out to the community. So remember that date. We're going to talk about that start date. So quite in short, why did that specific operator decide to go to remote PHY? We talked a lot about the reasons to go to remote PHY in previous webcasts, and I think these are kind of representing reasons on why would anybody want to go to remote PHY. But specifically for that operator, the transition to digital fiber, the ability to send down digital signals on the optics deployed out there, that was a big driver for them to be able to make the transmission, the transport layer, more efficient. So sending more lambdas and sending higher throughput on those same cables was one of their drivers for moving to remote PHY. Another big driver was the head-end space and power reduction that came from a remote PHY architecture. So moving things out of the head-end and the hub down to the network actually clears out some space and helps with the power inside the head-end. It does move that down the line, right, closer to the subscriber and into the network, but it does free up this expensive centralized location. Other reasons were DOCSIS and video services convergence. The customer wanted to converge their services as much as possible and be able to leverage the ability to send DOCSIS and video signals from the same platform, right? This is debatable, right? There are some others that make other choices on this subject. They wanted to have a better path to virtualization, and they wanted to get to some operational simplicity. And we're going to talk a little bit on how did that project really achieve those goals. Another goal here is a better SNR at the end of the line. Being able to get to the customer with a higher signal to noise rate is one of course, a driver for every cable operator when they want to transmit more data in a greater quality down to the subscriber at the end. So just in quick overview, we did a lot of testing. It took a while to bring up, the environment. As I said, the testing of the project really started when the remote PHY spec was not completely stabilized and closed. So we took our time with some testing. You got some example here on the architecture that we have set up in the lab in order to test the equipment. In the end, the actual deployment itself was very gradual. There was the first node that cut over was the one that took the most time, obviously. And then they grew it gradually to 4 nodes to, many, many more after that. But that gradual deployment, that kind of very slow ramp up is something that really helped with solving problems, fixing them for the future, and kind of really ramping up on the network resources, on the training for the team, and on setting up the real work processes that were required in order to be successful deploying this project. So if we look at some of the results, right, and we don't have time enough to review all of the results here, but basically the transition that specific example was from an MCMTS type architecture to a remote PHY architecture. And we kind of counted very crudely the amount of devices that were in the head end before the transition and after, and also counted the amount of watts that were used inside the head end before and after. So not going to go into too many details here, but you can see that the actual saving inside the head end and hub was quite significant, right? Over 3x saving on the space, and over 2x saving on the power consumption inside the head end when transitioning to a remote PHY architecture. And this is quite substantial, right? Not only do you save on space and power, but also the amount of devices that are being used is quite significantly reduced. And that number also helps with reducing the operational complexity of operating the network, right? So removing devices, converging more devices into one, all of that really did save actual dollars and money, but also really helped with simplifying the network operation. So the key benefits from the remote PHY migration were, first of all, the space and power savings inside the head end and the reduction in the number of head ends required. This goes a long way into the future when you think about, later on we will be able to move to virtualized hardware also inside those head ends, and even save even more on the amount of space and power that is required within the head end. So just think about, and this is an interim step, there will be additional cost savings going forward. And this is, again, saving right now today on space and power, but in the future, it will also help with virtualization of the environment, consolidating more hubs and head ends into one potential bigger data center that can be used on the same off-the-shelf servers and so, and be more converged in terms of service convergence, and also be orchestrated as a unified set of elements. Another benefit from the remote PHY deployment was the improved operational simplicity. The amount of devices that had to be eventually configured and managed was reduced quite significantly when we talk about the remote PHY, because now we had to talk to the Mac core, and all that configuration trickled down to the remote PHY devices. Now, you must think yourself, all right, we have so many more remote PHY devices in the field. How does she talk about improved operational simplicity, right? The point is that, yes, there are many more active devices out there in the field, but now we have better tools and better ways to manage them as one single unit. So it is true that they are distributed and closer to the subscriber, but we have better tools and orchestration and automation mechanisms to be able to manage them in a much easier way than previously those types of systems have been managed. So the reduction on the amount of devices, and eventually also the automation and orchestration tools that we have introduced, really helped with improving the operational simplicity. And testimonials from the customer said that, oh wow, it takes us a few minutes to install a new node, a new service group now, something that has taken us many hours in the past. Another benefit is the fact that we have moved to a remote PHY architecture helped facilitate an upgrade to the DOCSIS supporting network. And the DOCSIS supporting network are actually the fibers that are deployed out there in the field. So customers may take the advantage of moving to remote PHY to also upgrade some of those fibers that are the infrastructure of their network, and also improve some of the routing capabilities to be able to send those digital signals across all those fibers in their network. So normally a remote PHY project would also trigger some other improvements to other relevant systems that are supporting the DOCSIS network. So that can refer to infrastructural items, but it can also refer to tools and back office systems that can help manage the network more effectively. And in the end, one of the key benefits we got is better signal to noise ratio in the upstream. And that was an interesting result of this kind of test case, because we have measured the before and after state of the signal to noise ratio. And what we've seen is that there was a quite significant improvement on the upstream noise ratio, but on the downstream direction, there was not a clear improvement. It was kind of averaged the same. The reason for that, and this is a very interesting result, because a lot of the reasons for which customers are doing remote PHY is to improve also the downstream signal to noise ratio, right? So the reason we didn't see a lot of improvements, we believe, is first of all because we've also changed the frequency span in which the downstream signals were deployed. We moved those up the chain a little bit, up the frequency spectrum, and in the higher spectrum there were more challenges there. So eventually the noise levels kind of remained the same even with the remote PHY. And another potential reason is that our measurement of that signal to noise ratio was coming from the cable modems. We didn't really actually change those cables inside the home, and in the last, I guess, 100, few yards or meters up to the home, right? So these cables remain the same. They could potentially introduce some noise levels that could interfere with this transmission as well. So these are potential reasons why we've only seen the improvement on the upstream, although we are pretty sure that we need some more wider measurement case to be able to really determine the results on that.
Yeah. I know I had seen a slide from your expo presentation that had shown the improvements between upstream, downstream, before and after. Did you have a slide in your presentation for this or not?
I did, yeah. I tried to cut down the slides because we didn't have enough time, but I can unhide it for a second.
Because I think that slide is that is such an amazing slide.
Okay, yeah, let's do that. 1 second. Yep. Right. I tried to be brief, Brady. Remember that.
Sorry, I just love this slide so much.
Counted my behalf. I should have guessed.
So
All right.
can you describe this for people who will be listening to this on a podcast only version?
Sure. Yeah. So this is quite chaotic, right? So it's not a very clear picture. But our measurement showed that on the upstream direction, we have seen a 2.5 average improvement in the upstream, 2.5 dB average upstream increase. Right, so where the max value can be up to 8.2 dB of improvement, which is quite significant improvement, right? So an average 2.5 dB improvement on the upstream. On the downstream, we remained pretty much the same. The downstream SNR did not really improve by much. And I have a couple of diagrams here that show the noise levels as they are measured from cable modems within the, on the downstream from the cable modems and the upstream from the head-end devices or from the nodes. And we have that measurement here, and it's kind of, clear to see that on the upstream you have a very nice diagram of moving to the right to the to higher levels of SNR, whereas on the downstream direction you see it a little bit more dispersed, and we don't see this quite significant, this clear picture that we see on the upstream. And again, we really do believe that this comes from the end of the line kind of interferences that we're all struggling with, right? I know, Brady, you are specifically focused on helping with that, and I know that Asaf and John must have same thoughts as well. So these are interesting results, and more results are due really to understand how much are we really improving the SNR in both upstream and downstream in the network for remote PHY.
Can I ask a question on this?
Yeah,
I mean, we already dove. I mean, it's an interesting conclusion or results. And one of the things that come to my mind is typically when you go fiber deep and you go remote with DAA, specifically with remote PHY, is you have smaller service groups. And I'm wondering, in the upstream with the smaller service groups, you just have less noise aggregation in the upstream because you have less modems generating that. Now, I'm not a PHY expert, but I'm wondering if that smaller service group size doesn't help out specifically on the upstream SNR improvement as kind of a side effect of that.
It definitely could, and it's not to be ruled out. I don't remember the size of if the size of the service group has changed significantly on this example. I think it didn't, because the measurements were done. There were no splits in the middle, but definitely this is a good point, right? But we definitely need to consider that as well. When you reduce the size of the service group, definitely there will be less interferences. I definitely agree with that.
Yeah, I mean, the kind of the bottom line is going to digital fiber, you get rid of the Achilles heel, which is the analog fiber. Most RF plant HFC systems are kind of hamstrung because of that analog fiber. But if you're doing a node plus 5, then who's to say that 5 amps and cascade, that aggregate downstream noise figure becomes, relevant. For Tal, for your situation, was it a node plus 0, node plus 3?
This one was a node. Yeah, it was a node plus 3 example. So.
Yeah, so I mean, maybe the fiber was never the limiting factor on the downstream. On the upstream, I would definitely see a huge improvement because of the laser clipping effect of analog lasers and the loading on the upstream. Asaf, for your inquiry about the service group being smaller, someone brought this up 20-some years ago when I was at C-Corps, and I'm like, wait a minute, that didn't make sense at all. They were trying to add the noise figure of every cable modem. Remember, cable modems are bursty. Their noise figure does not add in. Only one transmits at a time. So regardless if you go from one modem to 500 modems on the upstream, you don't add that. It's not 500 modems of noise figure added together. It's one at a time. Now, as far as ingress, it's a different story.
So I wasn't thinking about just the transmission of the modems. I was thinking about the noise from the home, the other things that aggregate from all the other noise that aggregates, not the modem noise aggregating, but the service group size aggregating up. I agree with you. The modems wouldn't aggregate their noise figures, but all just the aggregation of a larger service group.
Well, of course. You have that variable all the time, right?
Mm-hmm.
You don't know where it's coming from. But I would say, Tal, in her situation, maybe the downstream didn't improve much because it wasn't fiber deep. It was still node +3. Fiber deep to me is node +1 or node +0.
Yep, noise can be interjected from every point, right? Those amplifiers may be a little bit less optimal. The home cable can be less optimal. We can see interferences from, could be anywhere. And we didn't really touch, a lot of those last mile kind of devices and passive. So everything, definitely everything can impact that.
And I assume it didn't have an analog overlay, right? It was all okay. Yeah, that's a big problem too. People trying to do analog video overlay with remote PHY, and then they take the noise from the analog fiber and combine it back in with the digital fiber, and you know better than what you started off with.
Yeah, I agree. This example was converged video. Not just residential PHY services, but also the business services and other types of services they have on their network.
So another point I want to bring up with that, though, is the physical. This is sort of what I harp on, is the physical layer. Layer 1 is still relevant, even though we're going digital fiber and it's very forgiving than analog. There's still physical aspects of it that must be, maintained. And one of them is, if I go DWDM, you have to understand what the ITU grid means. You can't just take an SFP for ITU 22 and the receiver is at ITU 23, different wavelengths. Because remember, DWDM is very specific for the wavelength it's using, very tight constraints. So I've seen people mix and match the wrong transmit receiver pairs.
Yeah.
Okay, and we do have a question from Simon, and he said that the downstream changed frequencies on your slides that you were showing, Tal, from 722 and 906 megahertz. So he was asking if some of the spread could have been from LTE interference.
Definitely.
And so maybe that helped on some of the numbers we saw.
We think so. So the move of the signal. So we moved the downstream spectrum, the downstream signals from around 200 plus to 700 plus, right? The upper layer definitely is most susceptible to LTE interferences and other types of, these kind of noises. So for sure, it could be. We didn't really go through the effort of really characterizing that enough, but definitely this is a harder area to transmit in, and this may also limit our improvements here.
Yeah, and I also want to say thank you to Raymond for letting us know that the audio dropped out for a moment. That was an accident on my part, and it's now resolved. And thank you for letting me know it was back up.
Another good point about going to higher frequency. There's not. Brady, you and I have worked at Secor Electronics, and we've specified and quantified noise floor and tilt and preamp and post-amp and amplifiers, and we know higher frequencies are more susceptible to CTB, CSO, but with the pure digital lineup, you have more CCIN, right? Composite area to ingress noise ratio. So who's to say that going to higher frequency, you're actually getting a higher noise floor in the form of intermodulation distortion, right?
Yep.
It's not going to be added white Gaussian noise, but it would be CCIN.
Yep. Yeah, it could actually absolutely be that.
Okay.
So very good. Tal, did we interrupt you enough?
No, it's all good. I was really trying to stick to my time frame, but I love the discussion. It's really good, and you guys really hit the right points there. All right, let's go to the challenges, right? So I talked a little bit about the benefits. Some of the challenges we've seen came from the fact that we were early adopters, right? The remote the remote PHY spec stability was not as good at the time, meaning there were a few, I think IO7, IO8, whatever came after we started testing, and some things actually changed on the way the remote PHY implementation was kind of defined by Cable Labs. So we had some changes in the spec really during the period in which we were starting to test. So this didn't help. In addition, there were new elements of network planning, right? So when we talk about remote PHY architecture, we introduced the CIN router, the Converged Interconnect Network, which is the network that aggregates all the traffic from the MAC core and distributes it to the remote PHY nodes. Those routers that are the CIN network need to be planned for, right, and need to make sure that you choose a device that is right for your purposes. There's a decision to be made whether you go layer 2 or layer 3, and you need to plan your entire network architecture with these new CIN switches and routers on the way. Another new element is timing architecture, timing distribution architecture, meaning you have to be able to verify that timing and clock information reaches every end of the network, every remote PHY node in the end, and you have to make sure your network planning includes the considerations for the timing information to be sent and received kind of symmetrically, right, going forward and backward and returning, and also making sure that you have enough accuracy in different points of the network where you have grandmaster clocks and and slaves all over. So this is another new type of planning that was not done by operators before, and this took some ramp up of the knowledge and making sure that the right plans are put in place. And the last challenge is the change in field measurement tools. The remote PHY introduction moved things to digital, right? So a lot of potential analog measurement tools that were used in the past were no longer available, would not work in the remote PHY architecture. So, operators and us as well, we needed to make sure we know how to measure things in the field effectively. We know how to allow the operator to deploy effectively, aligning upstream and downstream, for example, and detecting problems quickly. So these were challenges we've seen through the project, right? And we managed to mitigate them, solve them. Some of them took a little bit longer, but in the end, these were all good challenges to have, and we invested the time in solving those problems. And I believe this has been repaid, right? So moving to my last slide here, and for the successful remote PHY deployment, if you are going to deploy remote PHY, first of all, start testing early as much as possible, even on similar devices, similar architectures, just to get to know the equipment. Planning is key, obviously, for the architecture itself, for the deployment process, for everything along the way. And gradual field deployment really helps you find the problems faster, fixing them for the future, and setting those processes across your network, across your deployment workforce, so that everything is going to be done in a similar kind of unified way. Invest in plant data quality. Make sure you know how you deploy your topology and collecting information about those nodes and amplifiers out there. Automate as much as possible, right? Automation and orchestration, as I mentioned, are really helpful tools for managing a distributed network. And the last and most important point is that good partnership helps. We've worked very closely with Stofa, this customer in this case, and we've had a lot of calls, a lot of weeklies, a lot of ad hoc calls to solve problems, make sure once we find a problem, we solve it fast. So I can't really emphasize the importance of good partnership enough. So that's it from my side. Sorry for taking a little bit longer, Brady, and I'm going to stop sharing now. I can answer any questions, or if you want to move to Asaf, that's really good.
It's a fantastic presentation, and I think we had some good dialogue in between. Any questions from anyone before we move on to Asaf? Okay. Asaf, are you ready to queue up your presentation?
Sure, absolutely. Great presentation while I'm queuing this up. I think, let me see here.
Ready? You find that share button.
Yeah, is it sharing?
Not yet. I think you need to get that present button going there. As soon as you have the present, there you go. It's starting to show up, and I'm getting your screen ready here. There you go. You're live. Go ahead, sir.
Great. So great presentation by Tal, and I think that our presentations are complementary to each other in many ways, and we definitely agree on the benefits of DAA and Remote PHY. And I also want to thank RJ Walker, who jointly authored the experience we had with deploying Remote PHY in a centralized virtualized CMTS deployment. And I can't emphasize the same thing that Tal mentioned, which is having a great partnership with an operator is a key to having success. So we want to thank them as well. I don't want to labor on some of the points that Tal already made, so I'll kind of go through some things and focus on others as needed. Obviously, make it interactive if you can. I'm sure you won't withhold questions. So for us, Remote PHY is a superset of things. In fact, you could use Remote PHY for centralized as well as DAA architectures. It's a protocol that's out there, and we're looking at the combination of virtualization as well as Remote PHY as covering different opportunities and footprints that are existing in cable networks together. So in this case, in our experience here, we're talking about a vCMTS deployment in the centralized HFC architecture, and we're going to talk a little bit about the different areas of consideration. Not only Remote PHY, but the compute location, networking, timing, ease of expandability, and operations. So if we kind of look at the architecture comparison, where the top is a traditional integrated CCAP architecture, and obviously this is simplified, what we're talking about here in this deployment is leveraging the outdoor plant that exists already, and then focusing on the change on the virtualization of the CMTS core, and then putting in a dense PHY shelf in different locations and getting the benefits which were mentioned about Remote PHY, which is saving space, power, and cooling, and operational simplicity by using the better tools available in such a deployment. And just let's focus on that piece right there. So the pieces that are left in this architecture are the CCAP core, okay, which is connected through the SIN. The SIN is that converged interconnect network that we were discussing earlier that connects the vCMTSs with the RPDs. I'm going to elaborate on the SIN. You'll see a more complicated SIN in a little bit from the deployment, from the real-world experience that we have in this case. But there's a SIN, whether it's connected very closely between the Remote PHY device and the virtual CMTS, or there's various hops of layer 2 and layer 3 devices. In this case, the Remote PHY device is a dense PHY shelf. So there's a variety of different types of RPDs that exist out there, whether it's a dense PHY shelf or a small PHY shelf that can exist in a remote location, or the classic Remote PHY node, which is for a DAA or a distributed access architecture deployment over digital fiber. So what we did here, and this is really, you could see the vCMTS now pulls up in the diagram, and the RPDs are lower down. Remembering that the RPDs in these PHY shelves are generating the RF to their existing outdoor plant. And what we have over here is a multi-level and different location set of SIN. So we're actually talking over layer 3 in this SIN. There's some benefits in this deployment. And we also had to use the network that was there. So we didn't have the opportunity necessarily to dictate all the different things around the SIN. And you see the redundant PTP or grandmasters for timing of the 1588 portion of that as well, connected into what we call our CREs or core routing engines. They're basically the fabric that connects all the vCMTS servers between each other. In this case, we were able to expand from one secondary hub to another, and eventually you could see how you can connect over the same type of SIN, not only secondary dense Remote PHY shelves, but also Remote PHY nodes in a pure DAA deployment. So migrating from a traditional HFC outdoor plant environment to a pure DAA type of fiber deep type of deployment, all by expanding to the existing network infrastructure and connecting back up into these virtualized servers. So there's a lot of benefit in this network infrastructure, and Remote PHY as a technology here is being used to connect between the cores. In this case, it's the vCMTS cores and these Remote PHY devices. Okay, some of the deployment details that I wanted to share I just mentioned over here about having the expandability. So I'll skip this slide and focus on some of the flexibilities that Remote PHY as a technology allow you to have coupled with virtualization. First of all, Remote PHY will allow you to co-locate, to have a variety of location possibilities. First of all, you can do the classic Remote PHY node in the outdoor. In this case, what we're doing is we're having PHY shelves and remote hubs, but you could have smaller Remote PHY shelves that are not necessarily dense PHY shelves, dictated by the number of service groups and the size of these remote hubs. And then, of course, you can have a centralized deployment, and you can see that where the R-PHY is being generated and how it traverses. And the connectivity between the vCMTS core and these different PHY devices is, again, all these the standard-based Remote PHY protocols. I wanted to mention that that this isn't that everything is standards-based here. So one of the great opportunities that we've had is the folks on this call with Cisco, ARRIS, and Harmonic. Actually, we have live deployments with each other, interoperating with each other, not only at Cable Labs but with real customers. So we all work and play together and have live deployments with live customers with in our cases different cores operating with Harmonic, Cisco, and ARRIS Remote PHY devices out in the real world. So in terms of the maturity and the deployment, you could see that there's been a lot of progress over the last year in terms of not only interop in a lab environment, but with real subscribers at the end of those devices.
Yeah, I think that's something that's really important for, and should not be in any way, shape, or form. Well, it should be really promoted. The fact that DOCSIS compatibility and that all these devices are following the DOCSIS standard allows cable operators to take advantage of that and have the interoperability. So I think that's a really important point that you're making, and just to highlight that is important for everyone to realize. So thanks for bringing that up.
Yeah, absolutely. I think the cable industry has done a fantastic job standardizing, not only with Remote PHY, but other technologies. But here's an instance where as the maturity of the standards come to play, and we all kind of align ourselves to the same interpretations and interoperability of it, that it transitions into, obviously, from lab to field trials and then to real world deployments. And the fact is, where we are right now is we do have real subscribers in real world deployments with obviously multi-vendor environments, which is a great achievement for the industry as a whole. I mentioned on the previous slide the variability and the opportunity to move the Remote PHY device. And now, from a virtualization point of view, you could also use Remote PHY. Once you separate the hardware from the software and you virtualize the software into servers, you can do co-location, obviously have everything in one hub as well. So there's a spectrum of opportunity of where you can put the servers. Over here, Tal was mentioning earlier the benefits of space and power reduction, and she actually had a very clear table of power and space reduction. In our experience over here, we were able to take 15 different hub sites worth of legacy CMTS gear and consolidate the data processing on the cores into one location. So from 15 sites to one site, obviously there's a space power benefit, but there's also a benefit for operational simplicity there, and managing the equipment at a single facility as opposed to across multiple facilities as well. And obviously orchestration and automation is a big part of that. How you aggregate the data and visualize that and monitor those equipment is also a simplification. I think that we all have the same perspective about planning and the network opportunities here. We've had experiences deploying over layer 2 or layer 3. So Remote PHY as a technology gives the operator the opportunity to leverage their existing network. Obviously, different planning and different configurations, but Remote PHY is flexible enough to accommodate both types of SYN networks, whether it's a very small SYN with very minimal hops to multiple hops and more complicated layer 3 networks. Our experience has been that layer 3 also provides some level of configuration management and scale that provides flexibility and protection as well, that the layer 3 approach kind of gives a few more benefits on top of a layer versus a layer 2, though we do have experiences, successful experiences with layer 2. Things to consider are traffic prioritization and capacity management across that part of the network. QoS is important to manage congestion conditions. Obviously, if there's excessive congestion, it will impact stable network operations. It has to be a managed network. They can't be just, even with QoS, you cannot have the highest priority sort of traffic, the control traffic, congested. You have to be able to prioritize that and have that control traffic make its way through at the right priority. In terms of timing, there's a spec around that, and there's definitely various ways of managing the timing. We have experience with aware and unaware networks and successful experiences doing that. The definition is really well spec'd out in the remote DTI version that also references IEEE 1588. But to summarize it, PTP aware requires that all the network devices be PTP capable and really restricts the latency and jitter specs to much tighter numbers. And PTP unaware, it could be a place to start for networks that don't have everything PTP capable. The phase and offsets convergence times will be greater because of that, some of the elements not being PTP aware, but they're not operationally significant in our experience. We think that they're fast enough for deploying. Which is what we do in a lot of these cases. The latency and jitter specs are not as tight, but they serve DOCSIS purposes just fine. If you use timing as a service, and you need to have much tighter requirements for, like, you could think of other network requirements, and potentially those timing as a service services that haven't been deployed yet might require PTP aware networks. And there's a variety of high availability products out there that provide reliability and best master clock algorithms out there to have a robust timing infrastructure. Operationally, again, the combination of all these tools that have been spec'd out give us better visibility, better experience, better uptime, and the thing that I wanted to mention is with any new technology, there's learnings and then operational practice. So of course there are challenges, but the more you learn and you make it into a routine, that experience translates into actually higher uptime and better reliability. Especially, okay, so these new tools are again, it takes some learning because it's new, but the fact is these new things are more powerful and provide much better capabilities that actually over time give you this operational simplicity that we talked about. The experiences we've had in either upgrading software or managing different operational aspects has been a reduction for doing things that have taken weeks. Our customers have told us have reduced their service maintenance windows or their operational testing from weeks and days to minutes. So there's already some great gains around that. This is my last slide. So my conclusion is, for our experience has been that existing cable footprints obviously will continue to grow and improve. We all know the environment the cable industry lives in with demanding broadband growth year over year. But obviously they can't be overhauled overnight in most cases, right? So you need to find a migration path. And Remote PHY and vCMTS technologies improve this tool set, and it allows the operators to basically, based on their appetite, what they're willing to deploy and what migration path they choose. But we definitely have an architecture and a technology that's available to deal with today's HFC architecture, but also paves a great way to DAA and fiber deep deployments. I feel like I've gone through these really quickly. I'm kind of cognizant of the time that we have.
That's okay. We got questions for you. I got questions already, Asaf, and if you want to stop sharing, we can also see your face again. So, I mean, one of my first questions for you is, and we also had this from someone who had written in and said, "Hey, you know, we know Asaf's coming back. We have questions on latency." So, one of mine is, when you start deploying R-PHY devices, does that automatically benefit latency or reduce latency, especially to gamers like myself and other gamers, and any service that really depends on reduced latency?
The answer is it depends, right? I think that It depends on the choices we make. There's, first of all, the latency that people think about sometimes is between the scheduler that is typically in a core and the modem because of the request grant interval and DOCSIS scheduling. There's other things, there are other services that the DOCSIS allows us to use, like UGS service flows that are used typically for voice. And there's also other activities going on in cable labs related to flexible MAC architecture as well as low latency DOCSIS activities. So it depends on what type of service you're speaking about and what the latency is. Typically, the propagation delay between the scheduler and the modem is not the only thing. And I think that, in fact, Cable Labs released a report in their low latency DOCSIS slides that they had. I think it was a Cable Labs webinar a week ago that showed that the dominant factor in the latency impact to gaming was actually the queuing. The type of traffic that is non-blocking or the types of queuing of the traffic that occurs based on the traffic that is transmitted. So in this respect, Remote PHY doesn't deal with that. So their Cable Labs conclusions were that for low latency DOCSIS, it's kind of agnostic to Remote PHY or flexible MAC from that perspective, or full duplex. So the experiences you'll have are similar. That's the conclusion. They're similar latency behavior as a traditional integrated CCAP environment, because the Remote PHY device does not have the scheduler in it. The scheduler itself is in the CMTS core, and then the distance between the CMTS core and the modem would dictate the propagation delay for the latency measurement there. And the maps would have to traverse that propagation delay.
Okay.
Typical latency measurements are, and I've seen reports from ARRIS and Cisco as well around this, are around 6 milliseconds for a traditional DOCSIS network.
Second question I had for you, you had mentioned Remote PHY shelf and then Remote PHY, which is just like the device that replaces the fiber node. If I'm a cable operator, what would be the benefit, or what's the trade-offs and benefits between a shelf and a Remote PHY node?
Well, I think the variety of physical platforms gives the cable operator an opportunity to have these, maybe in the MDU, maybe in a dense facility. Remote PHY nodes are typically outdoor devices that can be deployed in Node Plus 3, 4, Node Plus M environments, as well as fiber deep. So it's an opportunity to use Remote PHY protocols and technology and have the opportunities to either deploy them outdoor or indoor. Remote PHY nodes that operate in a DAA environment also dictate that you have an outdoor plant, that you go to digital fiber. If you want to use the same technology, let's say in the case that I just mentioned, these PHY shelves are a distance away from the cores. And we're using, again, the Remote PHY protocols to connect between a single location with all the cores and these dense PHY shelves. And then they're using their existing analog optics. They haven't changed their outdoor plant at all. And then if they choose, they can then augment their network with DAA nodes, let's call them, using the exact same protocols connected back over the same SYN. So it's just an opportunity of having indoor versus outdoor, and the different form factors of having dense PHY shelves versus small form factor remote PHY shelves. So it depends on the location and the hub, and basically those are the factors that would come into an operator's decision of whether they need a dense PHY shelf, smaller form factor PHY shelf, or Remote PHY nodes.
Okay.
So you mentioned, using the shelf for hub collapsing, hub consolidation. I would propose also that it could be used for, if you're doing node splits, and it's an analog cable plant still, you could do service group expansion. So if you have a CMTS that's limited on RF ports, you could put a shelf right beside the CMTS, and the shelf has more RF ports. Every downstream RF port is basically a service group. So you could convert maybe a line card on the CMTS that has an RF physical interface card to a digital physical interface card, and physically wire it up right there to a shelf that happens to have, a lot more service group. So it's really like you could do service group expansion right? So that's like three
Great point.
scenarios.
No, that's a great point, because the connectivity between the cores and these dense PHY shelves or PHY shelves, or however we look at them, is Ethernet. It's standard-based Ethernet running standard-based cable apps protocols. So the expansion ability there is exactly as you mentioned it. It's another tool in the box.
So Brady, I think this fits well into the beginning of our discussion here on the satellites that are providing the services to rural areas. Remote PHY shelves, or even nodes, would be a very good solution for those rural areas where you have a long distance between the centralized head end, and you need to reach there with digital fiber, and then you can put just a remote PHY shelf inside a small town type of deployment, and use that to potentially compete with those satellites, or maybe the satellites will win eventually.
So we just have to somehow get that technology to John so he can get a little better audio and video technology, and that would help so much for next time, for the next show. So we're at the top of the hour. All those are fantastic presentations, wonderful material. Any final questions or anyone before we wrap this up?
I wanted to kind of say, layer one of the OSI model, don't disregard it, right? And I call it the little things, patch panels, Asaf, you mentioned, and everyone says this, we save power by going remote PHY, getting rid of our transmit receive, our upstream, downstream chipset, and putting it out in the field, remote PHY. But some people would argue that you're now putting that power requirement in the field. The good news is we're getting rid of our analog and transmitter receiver in the node, which could be power hungry. And there's an industry standard to keep the nodes under 160 watts. So with newer technology, with an upgrade, doing digital fiber, digital SFPs, getting rid of the analog transmitter receiver, we are limiting the power out in the node. We're not just transferring that power requirement from the head end to the node. So the nodes are still, within a certain requirement, 160 watts. Even when we go FDX, we are strongly trying to keep that under 160 watts. So even with FDX and the echo cancellation and that technology, that's going to be a requirement as well. So that's kind of interesting there. Even though I am eliminating RF in the head end and no more splitting, combining, and all the RF cabling and all that, you are still splitting, combining digital, probably to a switch, to a router. So we still have to keep in mind the optical connectors, the switches. Those aren't free. Obviously, an RF splitter is a lot cheaper than an Ethernet switch and the ports that come along with it. So looking at the rack space for the switches, it's tighter. It's not so bad, but everything has a little bit of cost difference, right? Everything's not free. I'm just a realist. Breakout cables. If I upgrade some type of digital physical interface card to a 100 gig port, how do I wire that up if nothing else has 100 gig? Do I have to break it out? They do make QSFPs that go 100 gig to 410s. So I'm basically taking a 100 gig port and coming out with 40 gig. But maybe that's my limitation on my other equipment is 10 gig ports. Correct fiber and the SFP you're using. I can't take a 20 kilometer SFP and try to go 80 kilometers with it. And then in the same, the flip of that would be, what if I'm in a lab and I get an 80 kilometer SFP, a ZR versus an SR, short reach, or LR for long reach, and I use that 80 kilometer SFP on a 6-foot piece of fiber. In the lab, you should be using, multi-mode fiber with the short reach. So, there's still a limitation there. What I found interesting was the 20 kilometer, 40 kilometer, 80 kilometer SFPs, they don't really transmit any higher power. The receive side is more sensitive, which really surprised me as a physical layer guy. So the 80 kilometer SFP, transmit receive, the receive side is more sensitive. So going with an 80 kilometer SFP, does it require an optical attenuator if it goes short reach? Really, you need to look at the specs of the receive levels and what it's really transmitting. If you're going DWDM, keep in mind the ITU grid, matching them up. Understand single mode fiber versus multi-mode fiber. I've even had people patch in fiber to a patch panel and not know the difference between an angled connector and a flat connector. And if they go into a patch panel, how do you know what's on the other side of that patch panel? Is it two angles coming together, or is it an angle and a flat? So understanding, the difference between the angle cuts as well. And then you run into also the node. Is it LC, SC? What type of fiber connector do I really need there? Is it SFP? It's probably an SFP, but if I'm doing DWDM, it's probably LC or SC. Sam Charlie versus Larry Charlie. So just some things to think about. One more thing, redundancy. If I do a SIN, a converged interconnect network, basically the digital fiber, and I'm taking two different paths to get there, what happens if I fail over from a 100-kilometer link over to a 2,000, or let's say 1,500-kilometer link? That delay on the SIN, it turns out it won't affect the modem's time offsets because the time offset is on the RF side, which that hasn't changed. But the digital link has changed significantly, which will affect the station maintenance, that delay we talked about in latency. So there are some things we can activate to have some dynamic latency measurement, update a little bit faster so that it can reconverge faster and the modems don't go offline. So just some little things to think about.
Anyone want to touch that?
Can't touch this.
Well, John, I think that was a good wrap-up on the physical layer aspects. So, any last comments? All right.
I'll make a comment. I'll make a quick comment. I just want to say that it's been fun to see the spec evolve and taking it as an industry to the point where it is right now, where I feel like it's as a standard, it's mature, and obviously we're having different experiences across the industry, rolling it out in a variety of footprints and with different operators. So I think 2019 is a continuation of 2018 with a lot of growth and opportunity, and in particular with remote PHY and virtualization. So we're going from talking and presenting slides to real world experiences.
Yeah, I love the fact that we're talking about actually production and doing this live and actually rolling out product with customers. This is a wonderful step forward.
Yeah, open RPD too, right? I mean, interoperability through cable labs, that's been significant. Customers that might want to update the field to one vendor and the CMTS is a different vendor. So not, forcing someone to upgrade everything. You might stick with the CMTS and go with a different vendor for the RPD.
Yeah, these are all good points. So, all right. Anything else? Tal, we haven't heard from you. I'll give you the last word, Tal.
All right, thank you for that. I have to say it's very exciting to see how we deploy these new technologies, and I think I love doing this kind of paper and love doing this investigation because it's very important to also think about not only the technology, which is cool and innovative, but also how do we deploy it, right? Bringing it from the lab to real life to the field is very complex, and these are the types of problems I love to solve, and I love the fact that the whole industry is now solving these kind of problems. How do we actually deploy those, make those operational, productize those? I think we still have more work to do there, and looking forward to see what happens next.
Outstanding. Thank you. All right. I want to thank so much Tal, Asaf, and John from ARRIS, Harmonic, and Cisco for this fantastic presentation today. I think I got those all right somehow. This was a fantastic episode. Our next episode is episode 40. Wait. What? Yeah. ARRIS? Oh, I'm not going to bring that up. I'm not touching that. Just let it go. You had to go there, John. So our next episode, John, is episode 46, scheduled for March 15th. This will be a PNM roundtable, proactive network maintenance roundtable table with guest Larry Wilcott from Comcast, and he is also SCTE Member of the Year. Everyone remember that. And also will be Jason Roop from Cable Labs will be with us. So again, we always do our best to bring you just technical content from the industry, no marketing, no promotions, nothing like that. So if you like what you watch, please click the subscribe button on YouTube. Give us a thumbs up. We appreciate that. And if you listen to us on our podcast, please subscribe on your podcast so you keep getting the latest updates. We'll catch you next time. Great having you listen to us. So long, all. Thanks again so much. Bye-bye.